Perfect. We've connected. Hello and welcome. This is MAE 113, lecture in number 13. This is Calculus for the Liberal Arts. My name is Richard Kohar, and thank you for tuning in on this Monday afternoon. It's the 8th of February. Hopefully everyone can hear me okay. I'm not sure if something is happening, if it's actually connected properly. Okay, the audio's good. Excellent. Okay, and how is the video? Is the video coming through clear? Perfect. Okay. Okay. Let's see. Oh, and there was... Oh, yeah, no, I haven't been writing yet, sorry. I'm just dealing with making sure that can you all see what I'm doing, or we might be having some internet issues. Yes. I'm not sure if... Let's have a look. Yeah, is it working okay now? Because I think today what we're going to do is do some more chain rule. Okay, perfect. Okay, so we're going to do a little bit more of chain rule. So remember, chain rule, or derivatives, are rates of change. And what the chain rule explains is how to multiply meaningfully those rates together. Okay, so for example, let's say that we have Usain Bolt. And we say that he travels twice as fast as a train. And that train is going 3 times as fast as a horse. Okay. So then the question would be, how much faster is Bolt than a horse? So probably intuitively you should be able to figure what that is, but what do you guys think in the chat? How much faster is Bolt than a horse, according to this? Anyone else? Anyone in the chat? Maybe there's a little bit of lag. 6 times, at least in his own head. Okay, so we got 6 times. So the way that we would express that, and yes, you're right, it's 6 times. The way that we would express that then is we would say d by, so we will be the derivative of Bolt with respect to a horse. Okay. Okay, excellent. There must be a really long delay. And that's good. I see everyone saying 6. Perfect. So we have the derivative of Bolt with respect to a horse. And using our chain rule, what we're going to say is we can then say, what's the derivative of Bolt to a train multiplied by the derivative of a train to a horse. And so what's kind of nice is intuitively the trains cancel out, and then we would be left with Bolt over a horse. So that we know what the rate is, that Bolt is twice as fast as a train, and that for a train's going 3 times as fast as a horse. So it's 2 times 3 gives us 6. Okay, so that's kind of the intuition. I should probably, from last time, I didn't give at least some sort of intuitive reasoning for it. And so we've kind of used Bolt, train, and a horse to kind of show that there's some sort of relation, how to multiply rates. Maybe that's why there was a thumbs down from last time, that I didn't give a mathematical explanation for why the chain rule worked. So I'm going to say that if I have y is, say, like a function of u, and u is a function of x, and f and g are differentiable, and then we can have dy by dx is equal to dy by du, and then du by dx, and that's the chain rule. So what is the kind of intuition or intuitive proof? So again, we have dy by dx, and what we're going to do is using our definition of the derivative, just the basic one, which is the limit as the change in x goes to 0 of delta y over delta x. And then what I'm going to do is I'm going to split those. So I have delta y over delta u times delta u over delta x. So I can still do that as a fraction because I'm working inside of this. That you can think of that as I've just kind of rearranged it. Then I have a delta y over delta x. I'm multiplied by delta u over delta u. And because of the multiplication, it's commutative, I can rewrite that as delta y over delta u times delta u over delta x. So essentially what I've done is multiplied by 1. Then, using our limit laws, I can apply it to each of these. So I have the limit as delta x goes to 0. And I'm going to apply it to each of these. So this is the product rule of limits. So delta y over delta u times the limit as delta x goes to 0 of delta u by delta x. So I can write some parentheses around here. Now this is where it gets interesting. The part is I have a delta x over here, and I don't have it in that term. So, but delta u is composed of delta x. And so that's why I'm going to be able to write this. Delta u goes to 0 of delta y over delta u. I am going to make a little note. So that's that delta u goes to 0 as delta x goes to 0 because g is continuous. The reason why g is continuous is because I already said that g is differentiable. And we said that last time, that differentiability implies continuity. So I know that g is also continuous. Then, well, this is the definition of the derivative of dy by du times, and this is the derivative of u by dx. So that's kind of the intuitive proof. There are some technical details that need to kind of be ironed out, and that's where we get into like a second or third year calculus course. But for now, this is good enough for us to use. But it kind of gives you that basic kind of intuition of that we're able to kind of cancel out these dx's, or sorry, du's. So you're left with a dy over dx. Okay, let's do some more rates. Let's say this example. This example is based off of example 10, page 115 in the textbook. So let's say that the population of Kingston is increasing at a rate of, let's say, 2 people per day. that is a made-up number. I don't actually know how many people are moving into the city per day, but let's say it's 2 per day, and on today's date, so the 8th of February. Now, this is a real number. The metro area of the city and it's growing to, so the metro area of the city grows to keep a ratio of, so the metro area grows to keep a ratio of 1 square kilometer per, this was a real number, 82.3 people. Then the question is how fast? Why are people moving to COVID? It's Kingston. Oh boy, I know. Well, I mean, there are people who may have got a new job here. They might be relocated, military. Maybe they're retiring so that they're staying, they're moving here. So they might not be interacting, but so how fast is the area increasing per day on this date? So again, there's a couple of things that we can do. We should define what our variables are. So for instance, let A, that be area. We have P be the population. We can let T be the time. Okay, so then what it's asking is how fast is the area increasing per day on this date? So what it's asking for, so now that we've written out what we needed, what they're asking for is the rate, so D by D. So they were asking the rate of the area, so that's A, per day. So this should be maybe time in days. So there's dt. So this is what we're required. Now we're told it's increasing at a rate of 2 people per day. So that they're telling us is the population over time, dp by dt, is 2 people. Two people per day. What's the other piece of information that we're told? We're also told that the metro area of the city grows to keep a ratio of 1 square kilometer per 82.3 people. So that means it's the area, so it's the change in area over the change in population. And so that is equal to 1 over 82.3. So that's square kilometer per people. So dA by dt is equal to, now we can use our chain rule. We can actually split that up. So we can write dA over dt. And what is going to be the two variables, or what's going to be kind of our thing that we're going to multiply by is our change in population. So we get dp. So if you kind of think of it like a fraction, that your dp and your dp's cancel, and you're left with dA over dt. So now we can just simply substitute in our values, so that you get 1 over 82.3 times 2 and that is equal to 2 over 82.3, and this is approximately equal to 0.0243. And I can actually give you, because this is a rate, it's the square kilometer per day. So that would be how quickly the city is growing. So therefore, the city of Kingston, on the 8th of February is growing at a rate of 0.0243 square kilometers per day. Perfect. So is that okay what we've done so far? We've been able to use some applications in kind of growth. Basically, we're able to multiply rates together so that we can figure out what another related rate is. So the nice thing with chain rule, why do we keep calling it chain, is because we can actually keep applying it repeatedly over and over again. So, excellent. So here's an example. This one is, so probably just to make a note, like there's example 10 and there's page 115. So if you want to look at a different, like the example, I've just changed the numbers to fit Kingston. But if you want to read that through, again, there's that one. Let's do this example, which is example 9 from the textbook. This is page 114. And what we're asked is to differentiate this function. I have f of x. I have x squared plus 1 to the 20 plus 1 all to the 4th. And then they said, don't expand, because that would take a while. So how do we differentiate this? The thing to realize is that there's actually kind of 3 functions to kind of look at. I have this function here, I have this function here, and then I have run out of pens. Oh, there's pink. Let's try that. So there's 3 functions, and this is going to be like an outside function. It's outside. Here's the inside function, and here's a really inside function. So I don't know, we'll call it inner. So there's outside, inside, inner. So there's 3 functions that we can do, and what we're going to do is we have to do the chain rule on the outside function, and then we have to take the derivative of the inside function. And to do that inside function, I also have to take the derivative of the inner function as well. So what I'll do is I'll write this out slowly. So working on the outside function, I bring that out in front. So I have 4 comes down in front of the big outside, this entire thing. And this reduces by 1 degree. So this drops down to 3. And then I still have to take the derivative of the inside. And in this case, the inside is x squared plus 1 to the 20 plus 1. So I'll just rewrite everything that's in this on all of that. So I have x squared plus 1 to the 20 plus 1. Okay. So I still have to take this derivative here. So I'll rewrite this out again. Okay, so when I take the derivative here, really what this is saying, this one right here, this is d by dx of x squared plus 1 to the 20 plus d by dx of 1. Now this, the derivative of a constant is 0, so that goes to 0. So I'm left with the derivative of just this to work through. Now, when I take this derivative, again, I'm using chain rule. So I have 20 up here, so the 20 comes down in front. I have the inside right here, or the inner, as I have called it. So I have x squared plus 1. This reduces down by a degree, so 19. And yet, I still have to take the derivative of this inner function. So I'm almost done. So I have this. Now I need to take the derivative of x squared plus 1. And the derivative of x squared plus 1 is just 2x. So that is the derivative of this. So copying that down, that is what I get. And then Maria's question, which always should pop up, is, am I done? Am I done? Am I done? No, because there's some simple things that we could do. 4, 20, and 2. So 20 times 4 is 80. 80 times 2, or 8 times 2 is 16. So put the 0 at the end of there. So it's 160 x. So there's our x that we have here. So I've done this, and I've done that. So I'm left with x squared plus 1 to the 20 plus 1 to the 3 times x squared plus 1 to the 19th. And that, I believe, ladies and gentlemen, we are finished. Is there any questions about that? All good? So maybe can we take the derivative? Just in case, is there some magical rule? Oh, I like the term magical because that makes this all easier, that we will learn in the future, like the power rule made derivatives easier. Yeah, this is done. We're done here at this point. Is there? So the question that I'm having is there something that makes it easier for us in the future? And the answer is the chain rule is our sledgehammer to answer most of our problems. This is it. This is what this is nice, because what we've been able to do with the chain rule is we didn't actually have to expand this out, which is kind of nice. We didn't have to expand this out 4 times and then expand it all out, then doing our combined power rule and so forth. We were able to actually do this fairly quickly. So without having to expand it, we were able to come up with an answer within a couple of lines. Excellent. And of course, can we take the derivative of above? How do we know when we're done without having a textbook to tell the answer or you telling us? Well, how do we know? Well, some of it is intuition. So when you look at this, I'm seeing simple things that I could do. For instance, I'm collecting kind of these coefficients here, 4, 20, and 2. I can also write the x together, and that's where I got the 160 times x. This I'm not touching. I'm also not touching this. And the reason for that is these are, highly compressed as it is. I got something that's to the 19th here. I've got something to the 20th. And then not only that, I have that to the 3rd. This is in factored form. And basically that's it. Like, you see how much you can kind of quickly simplify. And if you can't, just leave it as is. We'll see. We'll do a derivative above. So, for example, in a test, we could do that calculation on the side to substantiate our answer to include with our. Yes. Make sure. I mean, it depends on how you like to express your answers, but sometimes, for instance, here, I wrote this because I'm running out of space here. I only have so much room on the table to show you. But if I was to do this on paper, I would, write out something like this. And for instance, I would say something like, I would put a star, and I would have a star here. And basically this is telling me, like, continue from here to see what I did for my work. All the time I'm showing you the steps, so you have to show me the steps on the test. Maybe I'll call this 3B, so that when I do scan it, that you will see it on my when I have the PDF of it. Okay, can we take the derivative above? And I am mindful of the clock. We have about 13 minutes. Can we take the derivative of above? Okay. So what is the derivative above? Well, that is f double prime. And this is a good time to review what the product rule was. So if I had the product rule, the product rule was if I had f and g, so f times g, and I took the derivative of that, it's the derivative of f times g plus the derivative, or sorry, f times the derivative of g. Or I should maybe write it maybe with prime notations. So I have f prime g plus f times g prime. So notice the pattern. The primes are being applied. So on the first term, it's the derivative of the first function. On the second term, it's the derivative of the second function. So when I expand this out for doing three functions, so I have f g h plus f g h plus f g h. It's the derivative of the first function in the first term. It's the derivative of the second function in the second term. And this is the derivative of the third function in the third term. Why am I telling you this for the product rule for three functions? Because I have three functions. I have f here, I have g here, and then I have h here as well. I should have given it a different letter because I'm using f, but that is what we're going to do. We're going to have to take the derivative like this. I have three terms that I'll have. Oh, I can do it like that. Perfect. So now that you can see, we're going to do the derivative of the first one. So it's d by dx of 160x times g and h we don't touch. So just write that out again. Plus, then I'm going to do my second term here, which is, so I'm not going to touch the first function, so 160x. This is going to have the derivative. Times, and then h is untouched. Plus, and now I'm going to write out the first two functions. And then I have to take the derivative of that last function here. So d by dx of x squared plus 1 to the 19th. So what have I done here? This is by the product rule. Okay, equals. So I don't have to worry about that anymore. So taking the derivative of that, that's easy now, right? Because that's just 160 times x. So that's just 160. And then I write out that, all of that again. Plus 160 x times, and now I have to take the derivative of this. So what I need to do is I need to take this derivative. Okay, now when I'm doing this, I'm using chain rule. So by chain rule, 3 comes down in front, and then I still have to take the derivative of the inside. Okay, so I can leave that alone, so I'll just rewrite what was there. Next, I have to take this derivative. So I can apply this derivative to each term. So I get d by dx, x squared plus 1 to the 20 plus d by dx to the 1. The derivative of 1 or constant is 0. So again, that cancels. And now what I can do again is by chain rule. So by chain rule, the 20 comes down in front, and that reduces by 19. And I still have to take the derivative of the inside. So d by dx. I believe you are missing a squared after the first term. Let me go look. A squared after the first term. Oh. Yes. Sorry. Gotta make sure, where was I differentiating? Oh, yes, I was doing this one. Yes, it should be 2 right here. Perfect. Thank you. Okay. And almost finished. There's the 19. And then I'm taking the derivative of this one right here, which is then just 2x. So I'm going to copy that down. So that's times 3 times x squared plus 1 to the 20 plus 1 squared. Thank you. 20 times x squared plus 1 to the 19th times 2x. Maybe I'll call this 3c. And we're almost finished. So I'm just copying this out here. And for this one, I'm going to do the derivative of that. So it's 19. And I have the inside that I can just copy down. This reduces by 8 from 19 down to 18. And I still have to take the derivative of the inside. So the derivative of the inside of x squared plus 1 is 2x. Now let me see what 3, 2, 3. Good, so I'm taking the derivative there. There's the derivative that I've taken in this spot. And this one's untouched. And here's my derivative there, so that's good. Okay, let's do a little bit of cleanup. I don't see anything in this part right here, so I'm going to leave it. Plus 16 times 3 is 48. 48 times 2 is 96. 96 times 2, another 2. It's 192. 192. Remember, I've done this there's 2 zeros. Okay, so it should be 19,200. I have 2 x's. So that becomes x times x gives me x squared. And then let me copy that down again. Oh, I gotta make sure. 20 plus 1 squared. Second. Okay. Okay. The other thing too is I forgot to copy down this third one right here. There we go. Excellent. Okay. I was wondering why this wasn't, because right here, oops, no, it should be right here that we're looking at. So there is my matching. Right here is my derivative. And then I also needed to copy down that. So that's where that had disappeared. So why is this important? Because now I have this term right here to also worry about. I have a 19 and a 19, which gives me 38. Plus $160, 19, and 2. $16, 32. 32 times 19 is 68. Okay, and putting that together, x squared to 3, x squared plus 1 to the 18. And Maria's has asked, I really hope the ones on the tests and quizzes will not be as complex as this. Probably not. But we were able to do it. But as you can see, that it's repeated application of the chain rule and product rule. And where do I find the map for this one? I'm not sure what you mean by the map. Could you expand what you mean by map? But I mean, repeated applications of the chain rule, for instance, of like say x squared plus 1 to the 20. If we take the derivative of that, I have 20 times x squared plus 1 to the 19th, and I take the derivative of the inside, so that's 2x. And still, again, if I take the second derivative, oh, never mind, bad joke. This is where kind of simplification also helps. So 20 times 2, that gives you 40x times x squared plus 1 to the 19th. And so then you're taking the derivative of the first function. Oh. Yeah, we can do that in next class for sure, because we've kind of run out of time. I just wanted to show something pretty quick in terms of doing a double derivative with a chain rule. So plus I have 40x times the derivative. So again, I have the derivative of 40x is just 40 times x squared plus 1 to the 19th, plus I have 40x times 19 comes down in front, x squared plus 1, 18 times 2x. And then we can simplify, so I have 40x squared plus 1 to the 19th. I've run out. I have 80 times 19x to the 18th. So there again, you can do it much. There's a quicker, there's an example where I can apply chain rule and the product rule in one question. But hopefully that answers your questions. If there's any more questions, the quiz is tomorrow. We have a quiz tomorrow on assignment 4. Assignment 4 is posted. If you have any questions, feel free to send me an email. And if that's all for today, have a good night.